All right, you guys can see me now, right? Okay, it looks like you guys can see me. All right, so I did change your homework date to the 29th. So chapter 32 is due on the 29th. And then chapter 33 is due the following Tuesday. I forgot what date that was. That was the 7th of December. Okay? And I need to get through the entire chapter today because of what happened last week. The power went out in this building and I couldn't teach the second half of the lecture, but I should be able to do the whole chapter today. Okay? And then on the following week, I'll do pretty much all of chapter 33. In fact, I need to do all of chapter 33 the following week. Okay, and then I can introduce, and I'll also introduce the lab. Okay. All right, so your last exam is on December 5th. Work on the motor lab and on the transient lab. Okay. I graded your labs. I tried to focus on grading your labs. They're in the baskets. There's a basket outside of my office, and so the graded labs are there. I wanted you to have the opportunity to get some feedback from me regarding the lab before you turn in the next one. So I highly recommend, if you get a chance to come here and pick up your lab, please do so. Like I said, there's a basket that says Physics 210 outside my office. Just pick it up. Pick up your lab and look at the comments. Overall, students did a good job in collecting the data and analyzing the data. There were little issues in how he answered some of the questions. And I sent you an email regarding that, so please take a look at the email. And I forgot to email you the answer to the last question on the lab. Most people are trying to do it the hard way. If you used it at series parallel, it would have come up pretty quick. So I will try to remember to send you the answer to that. I typed it out, and I just forgot to send it. Okay, so I'll send that one to you guys. So let's take a look at our last unit. We're going to start with chapter 32. And I will say this, in our last unit, the main focus is really chapters 32 and 33. Chapter 34 is a very quick chapter where I kind of go through it kind of quick because it's very plug and chug in terms of the problems. And so I don't spend a lot of time on it, mainly because the math, if I wanted to get into details, the math would get complicated, and I just don't want to do that. And it would also take a lot of time. So chapter 34 will be a quick chapter. So the last week that we meet, I have 3 hours to do chapter 34. I'll probably do it in an hour and a half. Okay, so we probably won't need to meet the full 3 hours unless there's something I need to catch up on chapter 33. Okay, so the last lecture of the semester won't be that long. So we want to look at these topics in this chapter, and they're important. We're going to look at our last linear circuit element called the inductor. Okay. Suppose I have a basic circuit with a power supply, a resistor, and let's put a switch in here. And if I close a switch, then the current will go like that. Now, what do you expect? If you plot current as a function of time, you would expect when you close a switch, bang, current goes up, and you have your value of I. Okay, and this is basically the power supply voltage over R. That's what you would expect. But in reality, that's not what happens. Because when you close a switch, you have a time varying current. For a short, brief period of time, the current changes. It goes from 0 to some value. Okay? It goes from here to here. Okay? But it actually doesn't really make this vertical jump. And the reason why is because if you have a changing current, you have a changing magnetic field. And the magnetic field, if you use the right-hand rule, will be out of the board. So you have a magnetic field coming through this area enclosed by the loop. That means you have a changing flux. And that means you're going to have an induced EMF because of Faraday's law. So the circuit itself will induce its own EMF. It'll act like there's a battery in the circuit that's backwards. And you see that in the figure in the slide. And so what happens is, when you close a switch, that induced EMF is going to cause this current not to go up instantaneously, but it'll cause it to go up slowly. How slow really depends on how big the changing flux is and how big the resistor is, and we're gonna look at that. Okay, so let's apply Faraday's law. Let's actually set this up. Let's do the integral. I'm going to leave that up. Let's calculate the integral of d dot ds. And that's equal to minus d phi over dt. So I'm going to integrate this. The electric field is going to be in the direction of the current in here. But in here, the electric field, which direction is the electric field here? Electric field points that way in the battery. Okay? If I integrate the electric field around the loop, I'm going to get, if I go this way, that, but that's going to be equal to minus d phi sub b dt. And so this thing is going to cause the current not to jump up instantaneously, but to rise a little bit more slowly. Of course, if you just have a simple circuit like that, it's hard to notice that the rise is not instantaneous. However, if I put a large coil in my circuit, then that's going to make a big difference, because then I have a much bigger changing flux through this loop. And that'll make the current rise more slowly. Now this term here is proportional to the changing magnetic field, which is proportional to the changing current. So the change in flux through the circuit is proportional to this changing current. And so there's really some proportionality constant that really links this guy to that guy. And if you do an experiment, you'll notice that the induced EMF only exists when I is changing, that the induced EMF has opposite the polarity of the battery, which is what I drew there. So this is an imaginary battery that I drew. I'm going to get rid of it. It is the result of a changing magnetic field. And again, it's proportional to di dt. Now for this circuit, the effect is small. For the problems that we did in the previous chapter, we ignored this effect because for most of the examples that we looked at, this effect was small. The only example which I did in the previous chapter where the effect was significant was when I had the two coils, when I had the two field coils hooked up to the scope. That was the only time where this effect was important. And I kind of ignored it. I swept the problem under the rug. Well, let's say I put a large coil in my circuit. And in fact, let's just focus on the coil itself. Let's just have a simple circuit with a power supply and a coil. And let's assume, or let's pretend, that the coil is ideal, meaning that this coil has no resistance. Obviously, it's not true, but let's ignore it. And then one can worry about its resistance later. And you are going to worry about it when you do the experiment. How does the inductor then affect the circuit? Well, it's going to affect the circuit in the same way, except it's going to have a more pronounced effect. So if I put this coil in the circuit, it's going to have a more pronounced effect than this loop because I have many turns, right? I don't know how many turns are here, but I have many turns. And they have the flux changing through all these loops. Okay? So this coil is called an inductor. And it's the last linear circuit element we're covering in this course. What's a linear circuit element? Well, first of all, the voltage across it is dependent on some constant times some function in a linear way. Okay? Just like for a resistor, delta V across the resistor is R times I. There's a linear relationship between the two. And so there's going to be a linear relationship between the voltage across this and some other function. It'll be di dt. So if I have an inductor here, I close a switch, I'm going to have a time, for that instant I close the switch, I'm going to have a time varying magnetic field. At that instant I close the switch. The coil tries to prevent the rise in current. The coil wants to maintain status quo. That's Lenz's law. And again, that's conservation of energy at work, right? And so the current then, again, like I said, is not going to rise instantaneously here. It's going to rise more slowly. So your current will rise in that manner. And we will write down the expression. We will write down the expression that represents I as a function of time in a little bit. Okay, so the current will rise slowly. Now, what does the voltage across this depend on? Like I said before, the voltage across the coil is going to be minus d phi dt. But we know it's proportional to di dt. And let's call the proportionality constant that links these two L. And so we can say that the induced voltage drop across the coil is minus L di over dt. We're going to call L the inductance. And we can measure the inductance. We can measure this by, well, we can do it in a scope. We can solve this for L. And L is always a positive number. A lot of times they use the script E, so we can write it like this. You'll see a lot of textbook write a script E for the voltage across the coil. So if you can measure with the scope the induced EMF, and you can measure di dt, you can get L. So experimentally, you can figure this out. Now, what is the unit of this thing? Well, you have volts over amps per second, which is a volt second per amp. It's an ohm second. That's the Henry. So the unit of this is the Henry. And this is the inductance.
Sorry, Professor, you said ohms are volt seconds are ohms, or
volt per amp is an ohm.
That's right.
And so you get the units of ohm seconds, and that's a Henry. I'm sorry, I ran out of space down there.
Oh, who's it named after?
Remember, in last chapter I talked about Faraday's law. I said two people were involved, Joseph Henry and Michael Faraday. So Faraday got the credit for it. But then, since Henry was working on the same topic, they decided, oh, we'll name the units of inductance after Henry.
Okay.
Yeah. I don't know. I don't know the exact history. If it's just because Faraday was the first one to publish it, or you'll find in history that the first person who finds something doesn't always get the credit for it.
Yeah, like DNA.
Yeah, or the phone. Alexander Graham Bell gets credit for the phone, but it was actually somebody else.
Yeah.
So.
Or the car, or whatever. Yeah.
Yeah. So that's just how it is, I guess.
Yeah. For Henry's, is it a capital H?
With a capital H, yes.
Okay.
So how can we measure di dt with an oscilloscope? Well, what I would do is I would put a resistor in my circuit. I'd actually have to do an experiment with a resistor in my circuit. And I know that the current through the resistor is the same thing as the current through the inductor. If I measure dV dt across the resistor, then the current, di dt, the time in which the time rate of change of the current is 1 over the resistance times dV dt. Now you're making this measurement in the transient lab. So if you measure this across the resistor and you divide by the resistance, then you get the time rate of change of current. So you can measure this. This can all be done on a scope. So this is the way to actually measure what L is. But we'll find out we can also calculate it geometrically. So I'm going to show you that too. Now, what does L represent? Like, resistance really represents an opposition to the flow of charge, opposition to current. L represents an opposition to a changing current. Okay? L represents an opposition to a changing current. And it plays an important role in electronics. There's a plot of the voltage as a function of di dt. It's linear. Okay, there's a linear relationship between this and di dt. Now L, what does L depend on? Well, we know that the magnetic field through a coil really depends on I and the geometry of the coil. And so this L really depends on the geometry of the system. And capacitance was like that, resistance was like that. So all three quantities, capacitance, and inductance, and resistance, they all depend on the geometry of the system. And some other quantities that are related to the properties of the system. For example, for resistance, it depends on resistivity, which is a property of the material. Okay. All right, let me go through this. By the way, the L, sometimes it's really called self-inductance, but we usually drop the term self and just call it the inductance. So now let's take another look at an expression for L. And I have a mistake in my notes. There's a symbol missing. So I'll tell you where it is. Let's take a look at the induced EMF expression. Okay. That first line on that slide is, there's something wrong with it. I'm not sure what I did to mess that up, but you'll see the correct version on the board. So the induced EMF is minus L di over dt. It's also equal to minus d phi sub b dt. Now be careful. I got to be careful here. This is the change in flux through. This is the change in flux through one coil. But if a coil has n turns, then I got to throw an n here for the number of turns. All right. This represents the time rate of change of flux through one coil, but usually a coil has n turns in it, and so I have to throw in an n there. Now here's where the mistake is in the notes. There should be a symbol like this. Okay, because I'm going to cancel out the dt's. And I'm going to look at these two terms. I'm going to cancel out the dt's. So if you look at the first line, right before this term, I wrote it backwards. Hold on a second. So right before this term on that first line, there should be like a symbol like this, or a colon, or a semicolon, to separate this part from this part. Okay, that's missing. So I apologize for that. What do you think we can do with that expression?
Integrate?
Yeah, I'm going to integrate. And the integration is easy because the integral of d phi is phi, and the integral of di is I. My constants of integration are 0. So I get n phi sub b equals L times I. And so L is n phi sub b over the current through the coil. And so I can calculate what the inductance of a coil is, of an inductor is. I can do it for various geometries. And I will say it's not always an easy calculation. If you look up in engineering books, or if you go on Wikipedia, you can find a list of the calculated inductance for various geometries. We're only going to try to do the easy ones. The solenoid's easy, and then I'm going to do the torus. That one's easy. Okay? So there's very few of them that are very easy to do. You can do kind of quickly. And the reason why is calculating this can be challenging because of the geometry. So that's the geometric way of calculating the inductance. So we have two ways of getting L. One is from theory, and the other one is from an experiment. Okay, so those are two ways, but these require measurements. Okay, these don't. Let's do a calculation. Let's do one for a solenoid. I want to use this equation to calculate the inductance of a solenoid. So now let's pretend that this thing is much longer than what you see here, okay? You actually have one in the lab that's like a meter long that we use for one of our experiments when we're in person. But okay, I want to write these equations down. I want to try to leave them up on the board for as long as I can. Okay, so that's how I can calculate L. I'm going to do it this way here. And sometimes I need both, just depends on the problem. Okay, so I have a solenoid. Now, the magnetic field due to a solenoid is mu naught times the number of turns per unit of length times I. And I'm going to use script L for the length of the solenoid because I have an L for the inductance. Okay. Remember, N is the number of turns per unit of length. And so I want to use this equation to calculate the inductance of the solenoid. So let's pretend I have a coil and I have a current running through it. What's the flux through this thing? It's easy because the magnetic field is uniform in a solenoid. I'm going to choose my normal to any one of these loops. Okay, I'm calculating the flux through one loop. I'm going to choose the normal to one of the loops in the direction of the magnetic field so that this is positive, because L has got to be positive. And so this dot product just gives me B. And then all this stuff is a constant. Well, what's the integral of dA?
A.
A, okay. So phi sub B is mu naught N times I A, where A is the cross-sectional area of the solenoid, whatever it is, it's pi r squared, right? Okay, right, because if it's circular, it's pi r squared.
Yeah.
I'll just leave it as A for now. Okay. I saw that in the chat. I didn't know it's Fibonacci Day today. Thank you.
I saw a video on it, so
I'm
made
sorry?
me think of it. I saw a video on it, and it made me think of it because I wrote the date. So.
Oh, okay. That's cool. So let's calculate L. L is the number of turns that the coil has times this thing divided by the current. The current cancels. Now we can write this different ways. For example, I can multiply the numerator and the denominator by L. And so the number, this N over L is another N. So it can be written either this way or that way, or without the L's on it. So that's the inductance of the solenoid. So it's pretty easy to calculate. Okay. Now, a couple of questions. Why must L be positive? Well, because if L is negative, then the induced EMF is going to add energy to your circuit, violating conservation of energy. So L has to be positive. So another question is, suppose we have a wire. You know, sometimes inductance is not wanted. Suppose we have a wire, this is not very long, and I want to wrap it around a core. I want to make a coil. How can I minimize the inductance when I wrap it around the coil? There's really a couple answers. Anybody want to guess? Well, here's one thing I can do. I can take this wire, bend it in two, and then twist it. And then wrap it around the core to form my coil. By doing that, I have two currents going in opposite directions. And so I have two magnetic fields that oppose each other, trying to cancel B. That makes your flux zero, that makes your L go to zero. Or it makes the L very low. Now another thing you can do, and hopefully you don't do this with your motors, you wrap two layers. In one layer, the current goes this way. In the other layer, the current goes the opposite direction. That's going to cancel the two magnetic fields. Or it's going to make it very small. And that's going to minimize the inductance. Let's do another example. This time we're going to need to use both of these equations. So we're given, just one second. The self-induced EMF of a solenoid, the length of a solenoid, the radius of a solenoid. We're given the current, and we're also given di dt. And we want to find the number of turns in a solenoid. Okay, so let me write L solenoid here. All right, so we're given the length, we're given the radius, and I'm writing everything in meters. We're given I. We're given di dt. We're given the induced EMF. We're given a lot of information. I want to figure out the number of turns in my solenoid. So I'm given information that I can use in this equation and this equation. So I have two ways of calculating L. I want to set the two equations equal to each other. By the way, remember, this is the number of turns per unit of length. So maybe I should write it like this. So that's another way to write the inductance of a solenoid. So I want to solve for N. So I'm going to move the L up here. And then in the denominator, I get that. And then I take the square root of both sides. So then n, I just plug in the numbers, is, let me get my notes so I can get the values correct. Okay. E is 0.0016 volts. The length, mu naught 4 pi times 10 to the minus 7. And I'm not going to, I guess I'll write the units in. di dt is 200 amps per second. And the area is pi times the radius squared. So when you crunch this all out on your calculator, you should get 48 turns. It's not really a solenoid, but that's a real solenoid would have a lot more turns than that. Okay? Questions on it? Most of the calculations you'll be able to do when calculating L, the math shouldn't be that hard, mainly because geometry gets bad real quick. Just 1 second. All right, I want to find the inductance of one more item, a torus. And I actually have a torus, toroid. Okay, donut-shaped coil. That's what it looks like. I want to find the inductance of it. But the only difference between what you see here and the problem I'm doing is the cross-section is rectangular, not circular. If we do a circular cross-section, the calculation is much more difficult. I don't want to do the difficult calculation, okay? Because you'd have to do the integration is kind of a pain. So let's do a simpler one. A torus or toroid with a rectangular cross-section. So here, and then the wires wrap like this all the way around, tightly wrapped. The magnetic field is uniform inside, and it either circulates clockwise or counterclockwise depending on the direction of the current in the wires. It's basically taking a solenoid and bending it around into a circle. A solenoid with a rectangular cross-section. Okay? So the cross-section looks like this. And let's say this is the center. And let's say that this distance is r. We know that the magnetic field for a torus or toroid is mu naught N I over 2 pi r. We derived this using Ampere's law. So as you go from here to here, the magnetic field does change. As your circle gets bigger, the magnetic field does change. And my goal first is to calculate this, I got to calculate phi sub b. And the magnetic field does this. I'm going to choose the normal in the same direction. But my magnetic field is not uniform over this whole area. My magnetic field here has one value, and my magnetic field here has another value. So I need to break up my cross section in terms of pieces over which the magnetic field has the same value. Now it has the same value in this direction. It doesn't have the same value in that direction. So I can break it up into a piece that's this high, which is called A, and this wide, which you call dr. So my dA is A times dr. And I'm going to integrate from here, which is r, to here, which we'll call r plus b. So this is r. That's r plus b. So when I integrate this, I'm going to get mu naught n I a over 2 pi. The integral of dr over r is a natural log. I get that. And then I take this and stick it up into this equation. My i's cancel, and I get mu naught n squared a natural log of r plus b over b over 2 pi. That's it. Questions on that?
Wait, wouldn't it be r plus b over r?
Oh, r, yes, you're right. Thank you. I don't know what I was thinking. Yes, thank you. That's a good catch. Are we okay, though? Are we okay now with it?
Yeah.
Okay, good. All right, so now we've learned a little bit about inductance. What happens when we place an inductor in a circuit? What happens when we place a coil like this in a circuit? So let me redraw. I'm going to draw a circuit that has an inductor in it. We want to look at I as a function of time. So let's put a switch here. Then I want to know what happens when I close the switch. I know that I is going to go like this. Okay, I know I is going to go like that when I close the switch. And there's going to be induced EMF. So if I integrate the electric field in this direction, I'm going to get if I'm applying Faraday's law, I get that. By the way, if I sum the voltage drops like as if I were using Kirchhoff's laws, the voltage drop, if you sum the voltage drops in the direction of the current, then this thing will always be negative. And so if we just go back and think about how we would use KVL, then this equation would look like this. As long as you sum the voltage drops in the direction of the currents, this is always a negative. I want to solve for I. What do I do? And of course, at t equals 0, the current is 0. What do I do to solve for I? I did it for the RC circuit problem, and I did it for a couple of problems last week. What's my approach? Anybody want to guess? Well, I have to solve a differential equation, just like I did for the capacitor problem, just like I did for the two problems I did last week. But I'm not going to go through the math. I've done the separation of variables. I've gone through the exercise. Going through it will just take time. And so I'm just going to state the answer. All right, so you end up solving a simple differential equation, and you will get that the current, and I'll write it over here, the current is delta V sub S over R times 1 minus e to the R t over L. Oops.
I remember you doing that now.
I'm sorry?
I remember you doing that now.
Yeah, okay. So, I mean, I didn't derive it in the lab, but I just wrote it down. But you can solve this. You separate the i's and the t's, and then you integrate and find your constants of your constant, only one constant of integration, and you get that expression. And at t equals 0, I is 0, and at t equals infinity, the current is this. Because what the current is going to do is going to do this instead of this. Okay? This is what will happen in a circuit. The bigger L is, the longer it's going to take for the current to build up. Like the RC circuit, right?
Yeah.
Except in the RC circuit, we're looking at the charge on the capacitor. Here, looking at the current through the inductor. And notice the units here. R is units of ohms, L is ohm seconds. So the denominator is going to have units of seconds. And so this whole thing becomes
with time. Right?
I'm sorry?
That'll cancel with time then, right?
Yeah, yeah.
Has no unit.
Yeah, and you have to have that in an exponential function.
Yeah.
Okay. Yeah, whatever is up here has to be completely dimensionless. And you can see that if you expand the exponential function in a power series, you'll clearly see why the exponent has to be dimensionless. So one of the things we can do is we can define, we did this for the capacitor too, tau as L over R. And so we can rewrite this expression in the following way. And so tau we then call a time constant for the circuit. Okay. So it's easy to say, for example, how much current is in a circuit after one time constant? That means we said T equals tau. Well, if you said T equals tau, this ratio becomes 1. E to the minus 1 is like 0.37. 1 minus 0.37 is 0.63. So after one time constant, you're at 63% of the maximum current. Okay? If you wait long enough, then I equals I max. So let's take a look. I'm sorry?
Why is it negative?
Where is it negative? I didn't say, what did I say? Anything about negative?
Well, just because it has, in the original I equation, you have e to the positive RT over L, and the second equation, you have e to the negative T over tau. I'm just curious where that negative came from.
Thank you. I messed that up.
Okay. All right.
Thank you. Gosh. Yeah, it's got to be a negative because it's an exponential. Otherwise, it'll blow up. Let's take a look at this at this expression, or either one of these two. I'm going to distribute this term through. Remember, tau is just L over R. And I want you to just pay attention to these two terms. This term always stays there. I mean, this term always exists as t goes to infinity. As t goes to infinity, this term disappears. This represents how the circuit responds when you close a switch. And so this is the transient part of your current. The other term represents the steady state. So when t goes to infinity, your current is this value. This is the steady state current. This is the transient response. And if you wait long enough, the transient response goes away. So how does the RL circuit affect a function that varies periodically like you see in the screen, a square wave? So I have it hooked up. So I have it hooked up different than in your lab. Let me see if I can zoom in. In the lab, you have the scope across the resistor. I have the scope across the inductor. Can you guys see the trace?
Yeah.
Okay, so if I go to channel 1, this is the power supply voltage. Channel 2 is the voltage across the inductor, and this is both. Now notice all you see is spikes, right?
Yeah. Then there's the lines across, but
Yeah. So this is the voltage across the inductor. If I had you make measurements with the inductor, you would see it would actually be kind of tough to make the measurements because essentially you see spikes unless I change my components of the circuit, so it takes a long time for this thing the current to build up. So let's say, let me change my inductance. Okay, my inductance went from 2 millihenries, from 20 millihenries to 1 Henry. Notice the big difference. It takes much more time for the current to build up.
yeah.
Okay, so this is the setup for your lab, except that you're looking at the voltage across the resistor, and so the resistor is the power supply voltage minus this. So you actually see a more slow increase in the voltage, and so it's much more easier to make the measurements with the resistor. If I increase the frequency of the signal, oops, I'm not doing that, sorry. I was changing the wrong thing. I don't know what it's doing. Okay, so if I increase the frequency of the signal, you'll see that I'm not giving the inductor enough time to build the current. And so you see you don't see the spikes. The spikes are gone. If I reduce this, we'll go back and we'll see the spikes. So as I increase the frequency, I'm not giving the circuit enough time for the current to build up. If I decrease the frequency, then the current will build up quickly, and all you'll see, you can barely see the spikes now, right?
Yeah.
Okay, so that just shows you how the frequency affects what how the current and the voltage across the inductor. Do you folks have questions on that? Okay, and also the resistor also makes a difference. Changing the resistance in your circuit will affect how the current builds in your circuit. Okay, so I just wanted to show you that. Let me fix the camera. Let me turn off my equipment. Okay, so let me say a few more things about the the RL circuit. So let me write down the equation for I again. And I'll write it explicitly in terms of R and L, not with tau. So if I know that current, what's the voltage across the resistor? Because the current through here, the current through the resistor is going to be the same as the current through the inductor. What's the current through the resistor? Well, I just got to multiply this by R, whatever the resistance of the circuit is. By the way, I'm assuming right now that the inductor has no resistance. Okay? Because otherwise this term would be the resistance of the inductor plus the resistance of the resistor. So I multiply this by R, I get this. Now, what's the voltage across the inductor? Well, there's two ways for me to calculate it. I can always use L di over dt. But I can also use Kirchhoff's law. I can just say this minus this equals that. In fact, that's probably easier. Because I can get the answer right away. If you like taking derivatives, you can. So you should be able to derive those yourself. Given this expression, you should be able to derive this because that's Ohm's law. And this from Kirchhoff's law. Oops. Does that make sense?
Yeah. Is that his current law?
This is the voltage law because I'm adding
okay.
voltages.
Oh, okay.
Okay, so now let's take a look at energy. Let's go back and apply Kirchhoff's law again from the beginning. So this is the time rate of change of flux, okay? And this is what's inside my circuit. So the power supply is delivering energy to my circuit. The resistor is using it up. I'm going to multiply through by the current. So the rate at which energy is delivered by the power supply is lost by the resistor. In fact, it'll be more clear if I multiply through by -1. Let me multiply through by -1. This thing puts energy into the system. The resistor takes it out. But I have some left over.
Professor?
Yeah.
Do you not have to multiply the right side by I?
Oh, yeah, I did. I don't know what's going on today. I keep making these crazy mistakes. Thank you.
You're testing us.
Okay. I think it's just getting close to Thanksgiving. Okay, so this is the rate at which energy is put in. This is what's being lost. This is what I get what's left. Remember, this is external to the system. So it's like if I take a spring and I stretch it, I do work on the spring mass system. And what have I done? I've stored energy, right?
Yeah.
So what's happening now is energy is being stored. In fact, this is a time rate of change of energy being stored. In fact, this is du sub b over dt. This is the rate at which energy is being stored. And if I get rid of my dt's, then I get du sub b equals Li di. Guess what I'm going to do?
Integrate.
Integrate. The integral of du is u. The integral of this is 1/2 Li squared. And so this is the energy stored by the magnetic field of the coil. So it sounds strange that magnets can store energy, because magnets don't do work on charges. Magnets can't do work on charges. So how can a magnet store energy?
Is it because of its like electrical aspects?
Yeah, what is the electrical aspect? I mean, if this doesn't change, nothing happens, right? Just like if you have the ball at the bottom of a hill, if its potential energy stays the same, nothing's going to happen, right?
Yeah.
But if this changes, what's happening to the magnetic field? It's changing. If the magnetic field's changing, what's induced? An electric field. The electric field can do the work. And so it's the induced electric field that does the work on the charges. So the magnetic field can store energy, and when this changes, the induced electric field does work on the charges. Okay? But if this thing doesn't change, nothing happens. Because magnets don't do work. Magnets can't do work on charges. Or I should say magnetic fields don't do work on charges. And so the energy stored by a magnetic field is given as 1/2 Li squared. We can write it a little bit differently too. I want to do this calculation. I want to do this calculation for the solenoid. Just want to look at the energy stored in the solenoid. And then I'm going to make a generalization from that without using any vector calculus. You're just going to believe my generalization. Now suppose we have a solenoid. And we know that the inductance of the solenoid, and I erased it. The inductance of the solenoid is given by that expression. Okay? And we know that the magnetic field for a solenoid is given by this expression. Let's calculate the energy stored in a solenoid. So U sub B is 1/2 Li squared, which is going to be 1/2 mu naught n squared A times L times I squared. I'm going to move this over here. So that's the energy stored by a solenoid. I want to look at this expression and compare it, oh, there's a squared term, to this expression. Isn't mu naught n squared I squared equal to b squared over mu naught? Isn't that true? Do you see that? And so I can write it this way. And so the energy stored in the solenoid what's A times L?
Volume?
Volume, yes. So this is b squared over 2 mu naught times the volume. And so I'm going to define little u sub b as the energy per unit volume so this is the energy density. Of the magnetic field in the solenoid. But it turns out that it's true in general that the energy density can be written this way. So this is the expression for the energy density.
Wait, sorry, I missed what small ub was.
UB is called the energy density,
Oh, okay.
the energy per unit volume. So U sub B we're doing the same thing here as we did for the energy density for the electric field. Okay? Doing the same thing. Now, if B is constant, finding the total energy is very easy, but if B is not constant, then the total energy is the integral of the energy density over the volume. Can you see that? Can you guys see that as a slide in the way?
No, it's just over the top of it. You're good.
Okay. So that's the energy density, and that's the relationship between the energy density. And so this expression is you integrate this over which the magnetic field is valid. So this is also the expression for the total energy. So one can, if they want, and I'm not going to do an example here. You can equate them. You can equate this. You can calculate, if you know B, you can calculate this energy and you can solve for L. Remember that L was also equal to N phi sub B over I. Sometimes this integral is easier to do than this integral. So you use this method, this equation, to solve for L, as opposed to this. Now, we did something like that for capacitance earlier than this semester. So it gives you another tool to calculate L. Because it's not easy to calculate, okay? All right. Now, let's consider the circuit that you see there. So we've talked a little bit about energy. We've talked about the RL circuit where the current builds up. What about the other case where I have a circuit with a switch, and then I have a resistor, an inductor, and I just have another switch here. Okay, so let's say I close the switch. Leave that one open. What happens? The current builds up. I wait a long period of time. If I wait a long period of time, the current then is going this way, and I is delta V sub S over R, assuming my inductor is ideal. By the way, when the current's maximized, what's the voltage drop across the inductor?
Say that again.
When the current's maximized, what's the voltage drop across the inductor?
Isn't it the resistance plus the L?
Well, L is different from R, right? Right. The voltage across L is L di over dt. So when the current's all built up, this is 0. When you reach steady state, the current stops changing, right? What's the slope here? What's the slope of the horizontal line?
Zero.
0. So this is 0. So the slope asymptotically approaches 0. So the voltage drop across the inductor is 0 after a long time. It acts like a wire. So inductors act like a wire after a very long time. Well, I gotta say, an ideal inductor acts like a wire after a very long time. A real inductor that has resistance acts like another resistor after a long period of time. Okay? Okay, so the current's flowing, et cetera, et cetera, et cetera. And what I'm going to do next is I'm going to say at the same time, I'm going to open this and close that. What's going to happen? Well, this has energy stored. And it's going to get rid of its energy to the resistor. And this thing wants to maintain the current in the same direction. So the current will still keep going this way, but the resistor is going to take the energy away from it until it's all gone. And so if I set up Kirchhoff's laws, the voltage drop across the inductor plus I times R equals 0. The reason why these are both positive is because di dt is negative, because the current will be decreasing. And if you solve for I, a differential equation, then you get this expression for the current as a function of time in this particular case. It's analogous to discharging a capacitor, but we're not discharging anything. Okay? So I naught is the current you had when you close the switch. Okay? So what happens to this energy? Where does it go? Well, I want to show that all the energy goes to the resistor. The resistor uses it all up. This is my current when I close the switch. Okay, that's the current when I close a switch. And the power dissipated by the resistor is I squared R. And I naught is whatever the current was when we started. And this is the rate at which energy is dissipated by the resistor. I want to find the total energy dissipated by the resistor, so I have to integrate. And I have to integrate from the time I close this 2 until all the energy is gone. Now, this integral is not hard. You're integrating an exponential. You get an exponential again. And then your constants come out. And so E sub r is going to be I naught squared r, and then divided by r over L. And I got a minus sign. And there's a 2 here too. When I evaluate my integral at infinity, what is this term?
0 or
0.
1. Yeah, 0.
Okay, so then, so the minus sign will disappear. The r's cancel. The L will come up here. So all our energy that's lost by the resistor came from the inductor. Okay? And I have this all in your notes. It just proves where the energy came from. The energy was stored in the inductor, and the resistor used it all up. Okay, so it's about 12:30. So let's come back at about 12:50. I'm going to do this example on inductors. This was if you look at the sample test, this was the problem from the sample test. It was an actual problem I used, and I like the problem, so I use this all the time because it's enlightening. There's a homework problem just like this. And so I'll go over this problem, and then I'll talk about mutual inductance and LC circuits, and really I'll be done with the chapter. So let's come back at about, let's see, what time is it now? 12:28. Let's come back at 12:50. Okay?
Okay.
And I'm going to stop my recording.